Okay, guys, we are starting our study again. So, this is our module 3, and the name of this module is Quantum Mechanics. AKTU subject code for this subject is KS101. This is for first year, first semester students, and KS201, first year, second semester students. For those who are doing M.Tech integrated course, the subject code is MKS202. So basically the name of this module is quantum mechanics. Quantum mechanics is also known by various names. For example, we also say quantum physics. Sometimes we also refer this quantum theory. Many times we will also come across with the word wave mechanics, etc. So quantum mechanics has many synonyms. Okay, but the question is why we are studying the quantum mechanics? What is in quantum mechanics? What new we will study in this quantum mechanics? What is new in this kind of new branch of the physics? So अब आप देखेंगे कि नेचर की स्टडी हम करते आए हैं और उसकी स्टडी के लिए फिजिक्स डेवलप की गई है जिसको आप बेसिकली क्लासिकल फिजिक्स भी कह रहे हैं. So in classical physics we study all about the nature at ordinary scale because whatever we can see, touch or measure, we study. So that study is considered in the classical physics. But if we are to study the things at very atomic or subatomic level, then classical physics doesn't help us. तो कहने का मतलब ये है कि अगर हम ऑर्डिनरी स्केल से नीचे स्केल की तरफ स्टडी करना चाहें तब क्लासिकल फिजिक्स जो फिजिक्स हमारे पास अवेलेबल है उससे वो स्टडी पॉसिबल नहीं थी. अगर हमें एटम की स्टडी करनी हो, सब एटॉमिक पार्टिकल्स की स्टडी करनी हो, इलेक्ट्रॉन प्रोटॉन न्यूट्रॉन की स्टडी करनी हो, तो इन दैट केस द रेलेवेंट और क्लासिकल फिजिक्स was not helping us. So a new physics was developed and that came in the name of quantum physics or quantum mechanics. So in quantum mechanics हम माइक्रोस्कोपिक स्टडी तो कर ही सकते हैं लेकिन माइक्रोस्कोपिक स्टडी भी हम क्वांटम मैकेनिक्स से कर पाने में सक्षम हैं. सो ये इस क्वांटम मैकेनिक्स का बेसिक फील्ड है जो हमें स्टडी भी करना है. सो लेट अस सी. अब अगर आप चीज़ों को बहुत एटॉमिक स्केल पे और सब एटॉमिक स्केल पे इलेक्ट्रॉन प्रोटॉन न्यूट्रॉन न्यूक्लियर लेवल पे अगर स्टडी करेंगे तो क्या उन इतने छोटे पार्टिकल्स को जिनको आप देख भी नहीं पा रहे हैं, जिनको छू भी नहीं पा रहे हैं, तो उनके बारे में आप एग्जैक्ट मेजरमेंट क्या कर सकते हैं? नहीं हो सकता. जो चीज़ इतना छोटा है जिसको आप देख नहीं पा रहे, छू नहीं पा रहे, जिसको महसूस नहीं कर पा रहे, उसके बारे में एग्जैक्ट एक्सप्लेनेशन, उसके बारे में एक्यूरेट एक्सप्लेनेशन, उसकी एक्यूरेट एनर्जी, पोजीशन, मोमेंटम आप उसके बारे में नहीं बता सकते. तो क्वांटम मैकेनिक्स फिर कैसे उन चीज़ों को डील करती है? क्योंकि चीज़ें इतनी छोटी हैं और इतने छोटे लेवल पे उनकी एग्जैक्टनेस हम डिफाइन नहीं कर सकते, इसलिए क्वांटम मैकेनिक्स की जो लैंग्वेज है वो प्रोबेबिलिटी की लैंग्वेज है. एट दैट स्केल, एट दैट एटॉमिक और माइक्रोस्कोपिक स्केल, only probability or expectation value can be considered or can be measured. So thus, in quantum mechanics, we study the various objects at microscopic levels and the language of quantum mechanics is the probability. So now the syllabus of this module 3. So here we will study blackbody and blackbody radiation spectrum. We will study Stefan's law, Beam's law, Rayleigh's law, assumption of quantum theory of radiation, Planck's radiation law. We will study wave particle duality, de Broglie concept of matter waves. We have to study Schrodinger's time independent and time independent wave equations, Born interpretation of wave function, particle in one-dimensional box, eigenvalues, eigenfunctions, and at last we will study the quantum effect. Compton effect. So in all these topics, few topics are very much important for exam point of view, though all the topics are important, but few topics are important for long answer type questions. For example, the first topic is Planck's radiation law. There is a long answer type question on this topic here, and usually it is asked. And then Schrodinger's time independent equations. There are two equations, either two or one of the two equations is usually asked. Third is particle in one-dimensional potential box. This is very important problem. Usually this is asked. And last is Compton effect. So these are the topics that are important for long answer type questions. Though all the questions, all the topics are important or equally important for us. So now the question is, what is black body? हमें पता है कि अगर कोई बॉडी अगर ग्रीन हमें नजर आ रही है, इसका मतलब वो ग्रीन कलर की वेवलेंथ और फ्रीक्वेंसी को ही रिफ्लेक्ट कर रही है। अगर कोई वाइट नजर आ रही है, इसका मतलब वो सारे के सारे जो स्पेक्ट्रम के कलर्स हैं उनको सबको रिफ्लेक्ट कर रही है, इसलिए हमें वाइट नजर आ रही है। एंड व्हाट हैपेंस इफ द बॉडी इज नॉट रिफ्लेक्टिंग एनीथिंग? If it is not reflecting anything, it will appear dark. It means that will appear black. So anything which is not reflecting any radiation, so there will be absence of color. We will not be able to see. So that the absence of color is black. So anybody which is reflecting all the radiations falling on it will appear white, and anybody which doesn't reflect anything or absorbs all the radiations falling on it will appear black. So if a body can absorb all the radiations at certain temperature, it may emit all the radiations. So this is a property of a black body. So a body which absorbs all incident radiations and no reflections happens and appear black, it may emit all the radiations at certain temperatures called black body. So in nature there is not a single body which is a perfectly black, but lamp black is 98% black. Only 2% is reflecting radiations, but 98% radiations it absorbs. But a scientist named Ferry has designed a model which is a realistic example of perfectly black body. So what has he taken? He has taken a double walled a metallic sphere. In this sphere there's a hole, and just opposite of hole there is a conical projection. So and the inside of this sphere is uh, polished by lamp black, and the outside is polished with the nickel. So what will happen now when any radiation will enter in this sphere? the it may fall many times. It may fall on conical projection, and the tip of the conical projection of the conic will scatter it anywhere in the sphere, so no radiation will come out. So this is a kind of perfectly black body. Whatever radiation you incident on it in this hole, no radiations will come out. So this is a realistic example of perfectly black body. Now let me show you the animation of this. So here, this is the animation of this perfectly black body. So whatever radiation is coming inside this sphere, which is lamp black inside, can never come out. So this may be considered or is a perfectly black body practically. So now we study the black body radiation spectrum. So what happens if we heat a black body? So in that animation you are seeing a black body is being heated and it is changing its color. It means it is emitting different radiations. So a graph is plotted between the energy emission per second per unit area. This is energy flux with respect to the wavelength. And we are seeing in this graph, as the temperature of this body is increasing, the flux is also increasing. But the graph is not constant. the graph of flux with respect to wavelength is not constant. It means is at different wavelengths and at different temperature also, the energy emission continuously is varying. The energy emission is not constant. So the whenever we plot a graph between energy flux and wavelengths, so a varying graph just like this, which are you seeing in this diagram, is observed. So what are the properties of this blackbody radiation spectrum? We will study this now. So here we will study the blackbody radiation spectrum. Earlier we saw whenever blackbody was being heated, so a different energy flux was coming out from the blackbody. So here a graph is being plotted, intensity versus wavelength. So this graph, the characteristic of this graph finally leads to the development of quantum physics. We will discuss this later on. So now let us discuss the characteristics of this blackbody radiation spectrum. So you are supposed to keep this characteristic in mind. Usually these are asked. So the first characteristic, the intensity of emission increases with increasing temperature. So as the temperature of the blackbody is increasing, the emission intensity is also increasing. As you are seeing in the graph, there are three types of graph here at three temperatures. So the peak value is increasing or changing as the temperature is changing. So the intensity of emission increases with the temperature. And then we are seeing at a particular wavelength, intensity of emission becomes maximum. So in each graph, there are three plots here. In each graph, there are three peaks. So every peak represents the maximum value of intensity, and this value of intensity, the maximum value of intensity, is at different wavelength. It means is the maximum value of intensity at different temperature will come out at different wavelength. The intensity of emission is not constant for all wavelengths. It is varying with the wavelength and with the temperature. Now further we see the peak wavelength decreases with increasing temperature. Here we see, just look at the curve which is plotted in orange. The peak value is at certain wavelengths. In green curve, the peak value here is arising at different wavelength. In red curve also the peak values arising at different wavelength. But you are seeing the wavelength corresponding to the peak value. As the peak value is increasing, the wavelength corresponding to that decreasing. It means is as the temperature is also increasing, the wavelength corresponding to the maximum value or peak value is decreasing. Therefore, the absolute temperature of the blackbody is inversely proportional to the wavelength corresponding to the maximum intensity. So this is basically a Bean's law in which the peak value of wavelength is decreasing as the temperature is increasing. This value is shifting or displacing. So later on we will see this will be referred as the Bean's displacement law. And lastly we see the energy emission per second per unit area in each curve is proportional to the fourth power of absolute temperature of this blackbody. So we know this is nothing but the Stephen's law. In early classes we have studied. As the temperature of the blackbody is rising, the energy emission per second per unit area is proportional to the fourth power of absolute temperature. So these are the basic characteristics of this blackbody radiation spectrum. So now we will further study this graph. सो हमने अभी ब्लैक बॉडी रेडिएशन स्पेक्ट्रम की करेक्टरिस्टिक्स को स्टडी किया हुआ है एंड इन दैट स्टडी we have found that there is a characteristics of this black body radiation spectrum that as the temperature increases, the wavelength corresponding to the maximum value of intensity decreases. This means the wavelength is inversely proportional to the temperature. So this observation was made by the Beans, and he established the relation between the wavelength and absolute temperature of the black body, and this relation comes out to be like this: wavelength corresponding to the maximum intensity is inversely proportional to the temperature. So this law is also called Bean's displacement law, because the wavelength is displacing towards the lower region as the temperature is increasing. Okay, now Wiens also found that the spectral energy density means the energy emission per second per unit area, is given by this formula. Basically, this formula is derived only for the region which is falling left to the peak value of the curve, the reason which is left to the maximum value of intensity. So Beans only could explain that part of blackbody radiation spectrum. So here we are saying that a spectral energy density is inversely proportional to the fifth power of wavelength or emitted wavelength from the blackbody radiation. So this is Bean's formula for energy density of this part of radiation. Now, so here we have to study the Rayleigh-Jeans law. Rayleigh-Jeans studied the right part of the blackbody radiation spectrum. Right part means the region which lies right to the peak value. So Rayleigh-Jeans found that the energy emission is directly proportional to the absolute temperature of the black body, and they successfully found a relation for the spectral energy density. Spectral energy density is the energy emission per second per unit area at a particular wavelength. So in this formula it is clear the spectral energy density is directly proportional to the absolute temperature of the black body and is inversely proportional to the fourth power of the wavelength emitted from the blackbody radiation. So in the successive slides we will find how Rayleigh engines developed this formula for the blackbody radiation. So we have studied up to now that blackbody radiation spectrum was studied by the different scientists, but this spectrum was studied in two ways. In a first way, only the left part of the spectrum was explained by Beans. In the second way, the right part of the spectrum was explained by Rayleigh and Jeans. But there was no any relation that could explain the blackbody radiation spectrum completely. So Max Planck was the first who developed a new theory to explain the blackbody radiation spectrum completely. So it it was the Max Planck who paved the way for the new physics that was named as the quantum physics. And we know that Einstein took the help of this quantum theory of radiation given by the Max Planck and explained the photoelectric effect and received the Nobel Prize. So here let us see Max Planck and Einstein relation. You know, there is a very famous picture taken in 1928 in Berlin in a science conference. So in the center you are seeing this as a Max Planck, and left to the Max Planck is Einstein and left to me is Nernst. On the right side of Max Planck is Millikan and right to him is Laue, von Laue. These are the five eminent physicists and all are Nobel laureate. So now you can imagine the status of Max Planck. He was the Max Planck who could develop this quantum physics, and the base of developing this quantum physics was the blackbody radiation spectrum. So now please study the hypothesis of quantum theory of radiation given by the. तो हमने ये देखा अभी कि ब्लैक बॉडी रेडिएशन स्पेक्ट्रम को एक्सप्लेन करने के लिए बीन्स ने और रेले जीन्स ने अपनी अपनी थ्योरी डेवलप की है. But no one could explain the blackbody radiation spectrum completely thoroughly. So Planck was the first to explain the blackbody radiation spectrum, but he made certain hypotheses for that explanation. So these hypotheses are known as Planck's quantum hypothesis, and these hypotheses form the basis for Planck's quantum theory of radiation. So let us discuss what these hypotheses are. So first hypothesis is, along with the material radiations, blackbody contains linear harmonic oscillators with all the possible frequencies. So in a symbolic diagram, you are seeing different uh, waves. So these are basically linear harmonic oscillators, and these linear harmonic oscillators can have each and every energy, every possible energy they can possess. So this was the first assumption. And secondly, he assumes absorption or emission of energy between matter and radiation. This radiation is these linear harmonic oscillators, LHO. Basically, we also says these linear harmonic oscillators, Planck oscillators. So Planck assumed that absorption of or emission of energy between matter and linear harmonic oscillator is in the form of small energy packets, or it is discrete, and these energy packets are called quanta or photon. So earlier it was assumption that energy emission and absorption will be continuous, but here Planck put forward the new idea, and he said this absorption and emission energy is not continuous, but it is discrete, and this can only be possible in terms of certain small energy packets, and the minimum value of a small energy packet is the h nu, and this packet of energy is termed as photon and quanta. So these are the two hypotheses that Planck made to develop black body radiation theory. So to explain the black body radiation spectrum, Planck developed a radiation law on the basis of his hypothesis. He derived a relation in the energy density of Planck's oscillator. So first he found the average energy of Planck oscillator. So this relation is this. We will find this relation later on, and the energy density of radiation is this. So this energy density relation is termed as Planck's radiation law. So this relation completely explains blackbody radiation spectrum. So basically Been's law and Rayleigh-Jean's law are the limiting case of this Planck's radiation law. So let us see how this Planck's radiation law explains the blackbody radiation spectrum and how Been's and Rayleigh-Jean's law are the part of it. So let us see. Here we come to understand that Wien's and Rayleigh-Jean's law are the limiting case of Planck's law. Here, this is the Planck's radiation law, and here in the slide we are seeing that Rayleigh-Jean's law explains the right part of the peak, the right region of the maximum intensity. So when we set this limit in the Planck's radiation law, the Rayleigh-Jean's law is derived, and in the same manner Bean's law derived the uh, Bean's law explains the left part of the spectrum. So this is for lower wavelengths. So whenever we put the condition of a smaller wavelength in Planck's radiation law, we find the Bean's law. So this is how Planck's radiation law completely explains the blackbody radiation spectrum. Now we are to derive the Planck's radiation law.